This should be a quick lesson reviewing the properties of definite integrals and what you can and cannot do with a definite integral. So some common mistakes, things that people think are true but are actually false. So we'll talk through the properties, we'll talk through the average value, and then we'll define the mean value theorem for definite integrals. So those are our goals for the time ahead. So some of the properties, many of them are logical properties. If you have an integral that has the same bounds, it starts and ends at the same place, that means that there's no area because you haven't gone anywhere. And so the conclusion of that is that the integral would be a value of 0. We have the additive property where you're allowed to add integrals. And again, if you think about area, if you think about A going to B, and then that area connecting from B going to C, then logic would tell you you can go directly from A to C, that you're just putting those two area pieces together. We talked about order of integration and how you can change the order with a negative sign. That the negative sign, if you put a negative sign in front of an integral, then it will make the bounds go, what normally would go A to B would now go the other direction. Okay, switches the bounds, the order of the bounds. The idea of a constant multiple. If you have any constant value, then it can come out in front of an integral as long as that value is a constant. Okay, so works for pi, it works for square root of 2, it works for e, any value that is a constant. You can do the same thing with a negative. A negative can come out front because a negative is just a constant of -1. You can add, you can subtract integrals as long as the bounds are the same. So as long as both bounds are a to b, then it is valid to add and subtract. It is not valid to multiply. There is no multiplication rule for definite integrals, even though some people will try it and it seems like you should be able. You cannot multiply integrals. You also can't divide integrals, only adding and subtracting. The max-min inequality, again, really helps, I think, if you think about area. If you think about the maximum of f, that's the maximum height, okay, the tallest. And then if you take that max height and you multiply it by the base, then this is going to give you a base times height of the largest rectangle. So the largest rectangle possible. Correspondingly, if you take the minimum of f, it's the smallest height. And if you take the smallest height and multiply that smallest height by the base, you'll get the smallest rectangle. And so the integral, which is the exact area, must be in between those. It cannot be bigger than the largest rectangle, and it can't be smaller than the smallest rectangle. That true area must reside somewhere between those two. And then we have the last property, which is the domination function. Basically, that is saying if f of x is always greater than g of x, if every f of x height is greater than every g of x height, then logic should tell you that this area is going to be under f of x is going to be greater than the area under g of x. And that should be a logical conclusion if you're thinking about area in terms of height. Also, if f of x is always greater than 0, so in other words, it's always a positive height, then the area will always be a positive value as well. Okay, positive height makes positive area. Unless you would, I guess the only other way you could get negative area with positive height is if you went backwards on your bounds. That would be one other way that you could get it. But assuming that you're going forwards from A to B, then, and assuming that the height is always positive, then the area will always be positive. So we'll have you apply some of these properties and see if it's possible to do that. You've been given 3 values of area. So the area of f of x starting at -1 and ending at +1 is 5. The area starting at 1 and ending at 4 is -2 of the same function. And for a different function, the area starting at -1 and ending at 1 under the h of x function is 7. So the question is find 4 to 1 on f of x if possible. And so we notice that these bounds here are going backwards. And if the bounds are going backwards, then the area is also going to be backwards. So if that area is under the x-axis, but we're going backwards, then the answer to that is going to be +2 because it will be positive value. All right, the next one is asking us to go from 1 to 4. And we see that we, -1 to 4, and we've got -1 to 1. And then we can connect that as 1 to 4, and that's legal to add those two things together. And so this will end up to be 5 plus -2, and so 3 is the value of that integral. All right, our last one is asking us what if the h goes from a -2 to +2, and we already know that going from -1 to +1 is 7. And so what happens if we widen the width? What happens if we go from -2 to +2? Some people might think that doubling the base means that you double the area, and so you end up with 2 times 7. But that's a false assumption. Just because we widen the base of something doesn't mean that it has this corresponding impact on the overall area. And so this one is not possible to determine with the information given, because we don't know what the shape of the function is. We don't know if it's symmetric. We don't know if there's some kind of constant pattern to it. We have no idea. We can also think of this arbitrarily when you don't have a specified function, but you do have variables or constants that are expressing what you have. You still have to think of it in terms of thinking about area. So if we're told that the area going from a to b under the f of x function is a plus 2b, that is the value of the area, and then we're asked to take that same thing and shift it up. Okay, remember that +3 is going to take that whole thing and shift the whole thing up. So we are taking this blob of area. Okay, we have no idea what a plus 2b looks like. It could, look like this. And it's going to be going from a to b, and it'll be above, or 3 units above. So we're adding on top of that a rectangle of a height of 3. And so the base has to be considered, that's b minus a. And the height is 3. So we're adding on to that 3b minus 3a worth of area on top of an area that's already a plus 2b. And so we can consolidate those values and see what we come up with. So it looks to me like we're going to come up with a total of 5 b's and then minus 2 a's. All right, now we're going to move on to mean value and the idea of what that signifies. Last year we learned integral over interval is the average value of a function, its definition. The way it's written here, it looks a little different because it's next to each other. You've implied multiplication. We are usually more comfortable with f of x, and the integral from a to b of f of x being over like this. Okay, so the integral over the interval. So in terms of calculating it, you're just going to set up the integral from 0 to 4 of 2 minus x squared quantity dx over the interval 4 minus 0. And so you would evaluate your average value that way. Okay, now I want to talk with you a little bit about what the implications of that is, okay? So if f of x is continuous, then we can define this average value. So I want you to think of it this way. F of c is, okay, so I know we're going to do like, we set it up like this, but I'm going to erase that in just a second. Okay. In order to calculate that, we need an antiderivative. And if you remember that we did the antiderivative was the capital of f. So I want you to think about that. It'll be the capital of f as your antiderivative, and b will be plugged in first, plus c, minus, and then the antiderivative with a plugged in, minus c. And of course, the plus c and the minus c are going to cancel each other out. And so we can really think of this like this. And so lowercase f of c can be found by uppercase f of c, b minus f of a over b minus a. Now, this should look really similar to the other mean value theorem that we learned, which is f prime of c is equal to f of b minus f of a over b minus a. This is the mean value theorem for derivatives. So we have two mean value theorems, and I just want you to look at kind of how the progression of that goes. Let me take that off. Okay. If we drop this down from f to f prime, then look what happens to the numerator, to the function, that the capital F turns to regular f. You can continue to do that. If you drop this down to f double prime of c, then the numerator is going to drop down to f of prime of b minus f prime of a over b minus a. You could drop it down again. These are all mean value theorems. There we go. Now, all of these are mean value theorems, okay? So you've got, this one is the mean value theorems for integrals. This is the mean value theorem for derivatives, as all the other ones, okay? You will be told, it has to do with differentiability. We've heard that something could be differentiable. And if it's differentiable, then we've got the mean value theorem for derivatives. But we also have been introduced to the phrase twice differentiable. And twice differentiable means both that one and this one are true. And if you have thrice differentiable, that means 3 levels of derivatives exist. And so you get that one, and this one. And all of those are all theorems that hold true and can apply depending on the differentiability of your original function. If you're continuous, okay, continuous gets the first one. That capital F of c, the f of c can be equal to, that there has to be a solution to f of c equals capital F of b minus capital F of a. That's integral over interval if it's a continuous. But if you've got layers of differentiability here, those layers can lead to all the other mean value theorems as well. In terms of visually what it means, the mean value theorem for integrals means that there is a rectangle that has the same area as under the curve itself. Okay, that the blue area and the yellow area are exactly equal. And the implication on that is that this area here would be exactly equal to this area here. And that the mean value theorem is telling you that you should be able to find C. You should be able to find C, which will determine the height at which that rectangle is created. That geometrically, that's what we're looking at. that the integral value produces an area that's curved, but that it's possible to find a rectangular value that's exactly equal with the same base, and we call that height f of c, the average height. So I sort of think of it as a fish tank that you've sloshed around. I think I told you this illustration last year, and the water is all wavy and everything. And so if we're trying to find the volume of that is the same as when the fish tank settles down and the waves are all smooth and the water is still. That the amount of volume in there is exactly the same. All right, so that is a quick review on properties of integrals, the mean, the definition of average value, and then how that average value is connected to the mean value theorem.